Welcome back. The purpose of this update is to transition from the 1.0 system that we've been using to the 2.0 puck kit system for converting from dielectric to air voids using pucks that are fabricated in the laboratory. So this first part, I'm just going to walk you through the different equipment that is required for this puck testing kit to work. To start, you're going to need a computer. In this case, we're using the same tough pad that you would use for the field testing, but really for this puck testing kit to work, you just need an Ethernet input that's connected to our concentrator box here, and then you'll also need an antenna cable that connects here from our antenna to the concentrator box, which needs to be plugged into a power source to work properly. And what we have here is the same type of sensor. I believe this is sensor 171. Yeah, 171 here that we use in the field also. It's the same GPR sensor, except now we're going to place it upside down and put the stand over the top of it. And this is going to allow us to do our dielectric to air void conversion. These additional pieces here are required to be able to complete the different steps. What we have here is the Delrin piece that we're going to place at the bottom, and this will remain in this location for the duration of the testing. And we also have another piece of Delrin here that's labeled top. This will be incorporated for our noise subtraction. And then we also have a small metal plate that's going to be used as part of our both surface reflection and time of flight measurements. We've also added, since the 1.0 version, a HDPE sample. And this is a nice piece of kind of quality assurance specimen where we know the dielectric of this specimen is 2.35, and this again should be written on your specimen when you're using it, and that gives us a good indication if our sensors are within spec, if they're within the reported dielectric of this sample specimen. And then we also have, similar to last time, our design voids puck, which we label 1. You can label it A, B, and C, whatever is most convenient for you, as well as our medium air void puck. We're labeling that 2. And then our high air void puck, and we're labeling that 3. So with these components, we're now ready to begin the actual testing process. Now that we have all of our components connected and everything powered up, we're ready to go into the software and start to put in the necessary inputs to store the data. So once we get to our main screen, once this collect button is green, you know you have everything connected properly and properly powered up. The first step we're going to complete here will only need to occur once per year or construction season, basically to store all of your data in a central location. So to do that, we're going to go to System Settings. Then we'll go to File Management. And then we'll go to Project Groups. Once we're into Project Groups, you can see we have 2020-Lab. This is where we stored all of our 2020 puck testing kit data. And for this training video, we're going to set up a new project group by pressing New. And then we'll go into the location where we can call a new project group name, and here on the touchpad we're going to put training. And enter. and save. Now you'll see we have 2020 lab, so you want to make sure you go into the correct folder where you want all of your different projects saved. So here they're going to be saved to training, and we can go back to our main menu. At this point, we have collect still lit up green, so we can go into our puck testing location for this specific project. It's always good when you see the correct serial number that lights up here. We have sensor 171 connected, and this is just a screen to let us know that our sensor has been properly detected. We're now ready to go into a new project. Within our new project, we want to select our project group that we just set up for this training video. So here we're going to go to a drop-down menu, select training, and the next step will be to put in the specific information for the puck testing kit for the pucks that we'll be evaluating for this training video. We're now into our group settings for the specific project we're going to test. The convention we use for the inputs here are basically all the necessary information to be able to associate the dielectric to air void conversion to the correct project. This includes new project name, road ID, project ID, mix type, mix ID, equipment operator, and comments. So now we'll walk through each of these inputs, which are also detailed in the training manual, Module 2.0. For the new project name, we put in information that includes both the highway number as well as the state project number we're on. We're actually going to input this information in individual locations, but we've found that having a project name that gives us both the highway number as well as the state project number is a good way to easily look up information quickly with all this information in one place. So the first part was TH25, indicating the current route for where the samples are from. Then we do a dash and add the SP number to this specific project. Since we tested on Highway 25 on state project number 1007-21, this is what we input for our new project name. And this will, all of these inputs will remain constant for the entire project that you're on. So if you do multiple tests within the same day or on different days within the same project, all of these inputs will remain consistent. Our road ID, again, is TH25, indicating Trunk Highway 25. Our project ID is our state project number, SP1007-21. The mix type is specific to your state's or agency's designation. In our case, all of this type of information is stored in our test summary sheets, and this is what we use to store all of our information. So going by this sheet, by putting in our mix designation, it gives us all the information, including mix course, max aggregate size, easels, air voids, asphalt binder grade, and all these sort of things that you like to keep track of for the various mixes. So this you'll want to do similarly for your specific agency. In our case, the mix we're going to test is an SPWEB 350 C parentheses MSCR. And again, this is specific to MnDOT, so you'll want to put in your equivalent mix identifier for your specific agency. Now when we get into the mix ID, this is from, again, our mix design report, and this is just a number that we use to keep track of which mix we're actually testing. So in this case, the mix ID is 0-2020-044. And this can allow us to cross-check back with our specific state's way of organizing all the data. Equipment operator is similar to the past, where we recommend putting the initials of the tester and any comments you might have about this more group level inputs. At that point, you're ready to save. And the system is actually starting to warm up now, and we're ready to move on to our more file level or test level inputs. So we'll press new measurement and start the next portion of this video. We've now made it to the file level or test level inputs. A nice feature about these inputs is that each of these values or fields are directly tied to each of your measurements. So each time you run a puck test and export the data, each of the inputs that you put here are on the same row as the dielectric and air void output corresponding to that puck. So it's a little bit busy in terms of how much is on this input list, but it's nice as an end user to be able to have the option to store all of this information. As you'll see as we go through these, some of these you may or may not wish to use, and in this case you can just leave it blank, and that doesn't hurt anything about the measurement itself. So let's get going. The name in this case is unimportant for us, so we just keep it at file and move on to the next feature, which is, or input field, which is date paved. For the specimens we're using here for training, the paving occurred on October 9th, 2020. So we're going to put the year first, dash month 10, dash day 9, and press enter. We're next ready to move to the field ID, which for MnDOT is our test summary sheet number. And again, this is our way of corresponding the specific sample from the specific day to the testing that we're doing. So at MnDOT, we do these samples every 1,000 tons, and the sample number from the test summary sheet here is 322. We'll press enter and move to the cumulative daily max density tonnage. And again, this is something that's optional. In our case, we like to track how much tons were actually placed as part of that sample. So we're going to put 962, which is the amount of tonnage that this sample represented on paving October 9th, and press enter. Our bulk specific gravity is a moving average. of 2.485, which is again tracked on our test summary sheet and an optional input. We have a location where you can put the temperature at gyration. In our case, that's 270 degrees Fahrenheit. We also have the option for an agency lab ID because these are contractor fabricated pucks and coming from the contractor samples. We're going to leave that blank for the purposes of these samples. We also have a location to put the target air voids. This is a SuperPave 5 mix, so it's a little bit higher with the target air voids here at 5%. And we have the spot for the sample ID. And this doesn't need to be very long because we have all of the information about the specific puck input in the other fields. So for our case, we keep it very simple and just call it 1, 2, 3, or A, B, C for the 3 samples, or puck samples from this test summary sheet sample of paving. So the first thing we'll test in terms of asphalt will be sample ID number 1. But before we do that, we're going to do our HDPE to make sure that our sensors are working properly. We also have a location here to indicate whether or not you're testing the top or bottom of the sample. This is a drop-down menu, so as you'll see later, we're doing a third test just to be extra thorough of rotating the sample 90 degrees, and we'll actually put that in the comment. We'll put a 90 here to indicate that the sample was rotated 90 degrees from where it was originally. So our first test here will be on the top of the HDPE specimen, so we'll keep that at a T. The air void content percentage, typically if you're following our procedure, will not be known at this point, where we're asking the contractor or whoever's fabricating the pucks to test them almost directly after they're fabricated and before they're dunked in the tank if you're doing a T166. And these fields for air void content, the software will allow you to input that later. So this is going to be left blank now, and we're ready to put our sample thickness in. This is something that's very important to get a precise measurement of your puck thickness. This value that you put here actually affects the dielectric calculation because it's based on a time of flight, and we use that to calculate velocity and thus air voids from the velocity. So what you input here should be something that's very precise. And right now we are advocating that you use the value that's output on your gyratory compactor at the end of the gyration process before you pull the sample out. And we're continuing to do research in this area to make sure we're getting the most accurate sample thickness to be able to get correct values for our dielectric. So through using this process, our height of the sample that we're going to test, sample number 1 is 114.49 millimeters, but since we're doing the HDPE sample first, it's actually already written on there for you when you get your puck kit, and that's a 77.5 millimeter sample. So that's what we'll be inputting here. At this point, we've now indicated the correct inputs that we want associated with our dielectric measurement, and we're ready to begin the actual testing process by pressing collect. Now that we've input the correct inputs for our initial test here using our HDPE block or HDPE sample, the first step we're going to go through is the same for all of our testing, which is called background on the software. And to complete this step, you're going to want to put your top Delrin specimen even with the bottom Delrin specimen. And you can do this by kind of pinching on the corners to make sure you have all 4 sides flush with each other. So once you have this set up in this way, you're ready to eliminate background noise with this step, and it's as simple as just pressing the button in the software. And you'll notice this process is a lot less pressure filled because each individual step can be done individually rather than trying to time it up like we did with the 1.0 system. So we're now ready to put our metal plate on top of the bottom Delrin specimen after we've removed the top Delrin specimen. And again, just press the orange button and it will turn yellow when it's in the process of doing the measurements. And at this point, we're ready to test the specimen. One thing to note with this first test is that we have a sample with a known dielectric, but this dielectric is quite a bit lower than what we experience with asphalt samples. So while this is a good indicator that your sensors are working properly, it's not necessarily equivalent to the type of accuracy you should expect for the asphalt specimens. So for this step, we're going to place our known HDPE dielectric sample with a similar method, making sure it's centered on the edges and pressing the orange lit up surface button. And each of these buttons light up to the corresponding step that you're on. And with this next step, you're going to keep your sample, in this case the HDPE sample, in exactly the same spot and center your metal plate and simply press surface plus metal. And one thing to note here is that for whatever reason, the first test of the HDPE seems to be slightly higher on average than what the target HDPE dielectric is, but that normalizes itself and levels out for the next subsequent measurements. So we're going to press surface plus metal here, and we get a 2.381 dielectric. So this value, true to form, is on the higher end. It's a 2.35 plus or minus 0.003. So as expected, the initial HDP measurement is slightly higher than the reported dielectric value of that specimen. But at this point, we're ready to save our measurement and move on to our second measurement of our sample, which is to take the existing specimen and then rotate it 90 degrees. We're now ready to move on to our second measurement of the HDPE. And in this case, we're going into our comments and putting 90 to indicate we're going to rotate the HDPE 90 degrees. And we're going to keep our tested side to top. And one thing to note here is that, strictly speaking, there really shouldn't be a difference with the HDPE, but we're going to mimic the steps that we'd like to do with our asphalt samples here. So similar to all the tests you do with the puck kit, you're going to start with your background measurement. And then you'll move on to your metal plate measurement. And now we're ready to get to the spot where it's going to be slightly different than our last test, where instead of having it at the same orientation, we're going to rotate it 90 degrees. And we'll do this with the asphalt pucks as well. And at this point, we're ready to press the surface button, and then finish it off with the metal surface plus metal button. And we're back down to a 2.348, which is right on the money for our dielectric for HDPE. So the last measurement we're going to complete here, we'll press save here, will be one on the bottom of the HDPE, and we're going to get rid of our 90 in the comments so we know that we have it back to the original orientation, but now we're testing the other side of the HDPE. So we'll quickly go through this process, and the more you do this, the quicker it goes. And you get the nice readout right away of 2.332, which is 0.02 lower than the target of 2.35, and within our range of tolerance, which is 2.35 plus or minus 0.003. So we're now ready to move on to our design void sample, in this case labeled sample 1. On the inputs, the only thing we need to change here is HDPE, and that is now changed to sample ID 1. I already have target air voids percentage of 5 input here, but this is the time where you want to make sure that you have the correct target air void percentage. And then also a very important aspect of this that we've mentioned before is you want to make sure you have the correct thickness of this specimen input, because that's going to affect your dielectric measurement. And right now we are indicating that this thickness should be input directly from the gyratory compactor into this software, but this is a subject of ongoing research, and long story short, it's more than just taking a caliper and getting your best guess of the thickness. It's a very sensitive measurement and of great importance to getting the correct calibration from air void to dielectric. So more to come on that later. So in this case, from the gyratory compactor, our output for sample number 1 is 114.49 millimeters. So we're going to put 114.49 into our sample thickness indication, and we're going to make sure our tested side is top. And you can choose whatever convention you want for that. For us, top means the top of the specimen is facing to the top. So we're ready to go to collect now, and we're going to go through the same steps we went through with the HDPE, where our first test will be just a background measurement to eliminate any intrinsic noise of the system. Second step, we're going to get our metal plate measurement. Now, third step, we're ready to place our specimen, and here it's important to remember the orientation of your specimen, because you're going to rotate it 90 degrees for the next measurement. And in this case, just having the number that's written on the top facing me is the first measurement in this series. So at this point, I'm ready to press surface, and then we'll end it with surface plus metal. And this should give us an indication of somewhere around 5.03 if it's similar to how I tested it previously. and we get 5.036 for the dielectric of our specimen 1. And again, I like to keep the specimens in the same orientation that I had them during the test. Press save and move on to the next step, which is going to be a rotation of 90 degrees of the same sample. So in this case, the only thing you need to change when you go back into the inputs, it will store everything else as the same, except we want to go into comments and put 90. And we're at 5.045, which is very good repeatability, and we're ready to move on to our third and final test with this specimen. And again, we're able to keep all of our inputs the same. The only thing we'll want to change is the tested side from T to B, because now we'll be testing on the bottom, and we'll get rid of the 90 in the comments section because we're back to our regular orientation. And if you remember, we were looking at a 5.03 and a 5.04 on our first couple measurements, and now we're at a 5.037. So we're in really good shape here with our system. And you can write these answers down as you do it, but this is all getting stored to an exportable file that contains all the necessary information if you're doing the correct input technique that we're showing you as part of this training video. So we're now ready to move on to sample number 2, which is a target air voids of 9%. So we're going to go into target air voids and change that to 9. We're going to change our sample ID to 2. And a very important step, after you've indicated the correct testing side, which is T in this case, we always go T, then rotate it 90 at T, and then flip it to B for bottom. But as I was saying, a very important input that actually affects the dielectric measurement, I can't stress this enough, is getting the correct sample thickness. And in this case, we have a 114.07. And once we've done that, we're ready to move on to the actual data collection. And lastly here, we're going to move on to our third specimen. And this third specimen, we removed 500 grams, as you know, from the procedure we're recommending for the puck fabrication. So this corresponds to a target air voids of around 13%. So we're going to update that here. I should mention that value is not used in the calibration itself. We want to get our accurate, actually measured air void content, but this is a good way to catalog these different specimens. We're now going to put sample ID number 3, and we're going to be testing top again. And again, we want to have the correct specimen thickness. This is something that is critical to the accuracy of the measurement. So we're at 113.1 as output from the gyratory compactor at the end of compacting this sample. So now we're ready to go to collect. One thing to mention here is that the more this technique gets used and we gain more confidence in the system, we may be able to reduce the amount of measurements, but for now we're recommending to do the full suite of 3 measurements on each sample that's fabricated. Now that we've completed those 12 tests with the HDPE and 3 asphalt samples, we can go back and check out the results. So to do this, you're already in your correct project group and project name, so you can go directly into measurements, and here we have the results stored in a table. In this case, we can actually go into the individual files and update the corresponding air void content. To do this, you go to File Properties, and you go into the air void content percentage location, and here you can put in 4.4, which corresponds to our specimen 1 air void content, and save. And here you see it populated on your table, and you'll continue to do this with each of the specimens. Of course, the 3 different specimen orientations, you're going to put the same air void content in each of those corresponding locations. Okay, so now we're ready to export the results. To do this, we'll want to go all the way back to our main menu, and we can go into our playback, which is similar to the field testing arrangement of the GUI. And once we're sure that we have the correct project name within this correct project group, we can go to Export Project. And you get a nice pop-up that says your export was completed successfully, and you can, just like you would with any other sort of tablet or computer, input your USB stick, and now we can take the results, which are in Documents and Lab Measurement Exports, and I like to just organize it by date modified to make sure I got the one that I just did. And we'll want to drag this copy or drag, whatever your preference is, to your USB stick. So we've now taken the USB stick and put it into our computer that has an Excel template that will allow us to not only get our regression coefficients, but it's also a good format to be able to do your field core validations and store all your data in the various tabs. So what we're going to do here is grab the measured air void content in decimal form and copy the corresponding dielectric values, and we're going to place these results in cell B41, and I'm going to copy in the same format to keep green indicating locations where you can put inputs for data. And then if you look up here, you can see the regression that's created using these results, And then when you add your field core locations, you can see how the field results correspond to your calibration to convert from dielectric to air voids. And this also gives you your coefficients A and B that need to be input into your field testing equipment to be able to do the real-time air void content or percent GMM output out in the field. So this completes our Module 2.0 training, and one last thing to mention as part of this is that all of these corresponding templates that we talk about as we go through the training will be posted to our DPS Pooled Fund website, and additional training corresponding to the field aspects of this template, including how to validate with cores that your conversion from dielectric to air void is correct, will also be updated on the website with the corresponding 2.0 training. Thank you.